All right, so our first topic for today is going to be power in multi-frequency circuits. And we're going to wind up using the following few trig identities. The first one is one that we talked about in our last class. So cosine theta 1 times cosine theta 2 is equal to 1/2 cosine theta 1 minus theta 2 plus 1/2 cosine theta 1 plus theta 2. Another one that we're going to wind up using is that cosine of negative theta is the same as cosine of theta. And our third one is going to be, bless you, sine of negative theta is equal to, not sure if we're going to use this one, but I'll put it in here just in case, negative sine theta. So, excuse me. Let's say that we have a generic circuit element like so. It has some current I of t flowing through it and some voltage V of t across it, where V of t is equal to Vm1 cosine omega 1t plus theta V1 plus Vm2 cosine omega 2t plus theta V2. So we're going to be dealing with two excitation frequencies here. And the current will then be of the form Im1 cosine omega 1t plus theta I1 plus Im2 cosine omega 2t plus theta I2. The instantaneous power absorbed by this element, P of t, is simply going to be V of t multiplied by I of t, because power is always the product of current and voltage. But as you can guess, when we multiply these two guys together, it's going to get pretty gnarly real quick. So what I'm going to do is I'm going to label these guys. So let's call this part A, B, C, and D. And so the first term that I'm going to have is when I multiply term A by term C, because I got to FOIL this guy out effectively. So using the first trig identity that we have, that would be 1/2 Vm1 Im1 cosine. So we'll have omega 1t plus theta V1 minus omega 1t plus theta I1 is just going to give us theta V1 minus theta I1. And then we're going to have a factor of 1/2 Vm1 Im1 cosine twice omega 1t plus theta V1 plus theta I1. Our next term will come from multiplying term B by term C. So we're going to have 1/2 VM2 IM2 cosine, excuse me, so now we're going to have omega 2 minus omega 1 t plus theta v1, excuse me, theta v2 minus theta I1 plus 1/2 VM2 IM1 cosine omega 2 plus omega 1 t plus theta v2 plus theta I1. Now we're going to multiply C by, sorry, so let me just be clear here. So this was A times C. This guy right here is B times C. So now let's do A times D. So that's going to be 1/2 VM1 IM2. Sorry, I just realized a mistake here. This should have been IM1. When I was multiplying B times C, I had VM2 IM2. That would be B times D. So, all right. So when I'm multiplying A times D, sorry. So 1/2 VM1 IM2 cosine omega 1 minus omega 2 t plus theta v1 minus theta I2 plus 1/2 VM1 IM2 cosine omega 1 plus omega 2 t plus theta v1 plus theta I2. So that was A times D. And our last term comes when we multiply B and D. So that'll be 1/2 VM2 IM2 cosine theta v2 minus theta I2 plus, excuse me, 1/2 VM2 IM2 cosine twice omega 2t plus theta v2 plus theta I2. So this is again for multiplying B and D. So this can be simplified. Yes.
In the last step, when you multiply A and D, is that at the cosine? Is that omega 1?
I'm sorry, that's an open parentheses.
Okay.
So you're adding omega 1 and omega 2 together and then multiplying that by t.
Okay, gotcha. Thanks.
Yep. So if we multiply these two voltage and current waveforms together, where the voltage waveform is operating at 2 frequencies and the current waveform is therefore operating at that same 2 frequencies, we find out that our power is now oscillating at 5 different frequencies, right? We have some DC terms. We have some twice omega 1 terms. We have some twice omega 2 terms. And then we have terms that are the sum of the omegas, and we have terms that are the difference of the omegas. So it actually might look like we have 7 here, but obviously we're let me do it in this term and this term can actually be combined because they're oscillating at the same frequency, since omega 2 plus omega 1 is the same as omega 1 plus omega 2. So we could combine those terms. And these guys right here, we have omega 2 minus omega 1. So the cosine of omega 2 minus omega 1 times t is actually the same frequency as cosine omega 1 minus omega 2, since cosine of negative x is the same as cosine of x. So we could, if we were so inclined, lump all of those guys together. We're not going to bother going through that. I just want to show you that this this instantaneous power analysis for multi-frequency circuits becomes very, very, very difficult very, very, very quickly. Our average power here, 1/2 Vm1 Im1 cosine theta V1 minus theta I1 plus 1/2 Vm2 Im2 cosine theta V2 minus theta I2 falls out of this pretty neatly, but there's actually a much easier way to get it, which is going to bring us to the topic of effective values, right? So this is our instantaneous power. I'm just going to explicitly write an equation here. P average 1/2 Vm1 Im1 cosine theta V1 minus theta I1 plus 1/2 Vm2 Im2 cosine theta V2 minus theta V1. We know that is the average power because it is the DC contribution to our instantaneous power waveform. and therefore it represents the DC offset or the average value of the system, just like it did when we only were looking at things at one frequency. Now, getting these results is fairly straightforward and it doesn't require a whole heck of a lot of circuit analysis, but in really complex circuits, effective values will actually get us there much, much quicker. So now let's shift our focus to the concept of effective values. So an effective value of a periodic voltage or current waveform is analogous to a DC voltage or current which delivers same amount of power to an arbitrary resistance. So really it should be the same amount of average power So what this statement really means is that electrical engineers got lazy, but in a smart way, okay? They didn't want to have to do all of that terrible computation that we just saw in our simple only two frequency multi-frequency circuit analysis. And so they developed a method by which to convert any periodic waveform to a DC equivalent that delivers the exact same amount of power. That is the RMS value that you spoke about, or we spoke about in circuits 1. So an effective value, V effective, for any periodic voltage waveform is given by the square root of 1 over the period of the integral over exactly 1 period of the periodic voltage waveform squared with respect to time. And we can say the exact same thing for current. So the effective value for the current will be 1 over the period multiplied by the integral of 1 period of the square of the current, waveform. These representations are commonly called RMS, or root mean squared quantities. And it's because we are taking the square root of the arithmetic mean of the square of the signal, right? So the mathematical operation involved here is we have our voltage waveform. We square it, because if we took the average value of a periodic waveform and we didn't square it, there's a distinct possibility that our answer would be 0, which would give us no actual information. So by squaring our periodic waveforms, we are always going to get some finite, usually non-zero value. When we integrate over 1 period and we divide by the length of that period, that is taking the average value, or the arithmetic mean, of the square of that voltage, and then we take the square root. So it's root mean squared, RMS, all right? So let's say, for example, that we have some voltage signal, V of t. And we'll make this a series of rectangular pulses. Having a maximum value of, let's say, 5 volts. This is going to occur at t is equal to 1 second. Then it goes back up at 2, down at 3, up at 4, et cetera, et cetera, et cetera, and repeating. This would be representative of a simple square wave, but with a small DC offset, really. Excuse me. We can actually find the effective value of this rather trivially, right? The V effective in this case, we're just going to literally throw stuff into our equation. So what is the period of this function? 2 seconds, right? So it takes exactly 2 seconds to complete 1 cycle. Does not matter if we start measuring from the leading edge of our rectangular pulse, or the trailing edge of our rectangular pulse, or the midpoint of our pulse. As long as we're integrating over exactly 1 period, we're going to get the right answer. So we would have 1 over 2 seconds. Because this is a piecewise function, I'm going to split it up into 2 integrals. We're going to have an integral from 0 to 1 second of our voltage waveform here, which is just what over that integral? 5 volts DC value. Square that. And then we'll have a second integral from 1 second to 2 seconds of 0 volts squared with respect to time. Now, obviously, we know that that second integral isn't going to contribute anything I just want to make it very clear that I'm integrating over the entire duration of one period. Obviously, when you do your homeworks, et cetera, you don't have to explicitly include places where we have a DC value of 0 or anything like that for some duration of time. I'm just trying to make sure it's very, very clear here that I'm integrating over one period. So that's going to look like the square root of 1/2 seconds. So that's going to be 25 volts squared t evaluated at 1 second and 0 seconds when I do that integral, plus 0t evaluated at 2 seconds and 1 second when I do this integral. So we can throw this guy away now very easily. And we'll have 1/2 seconds times 25 volts squared times 1 second minus 0 seconds is going to look like 5/2 volts. And I like to denote effective values using the units volt RMS, right? Actually, yeah, so 25/2 in my square root is the same as 5/√2, yeah. So we can see that the effective value for these rectangular pulses like this is just the amplitude of the pulse divided by square root of 2. This is only true when we have what's called the 50% duty cycle, meaning that the signal is on 50% of the time, or it has its high value and then it's 0 for the other 50% of the time. If we made our series of rectangular pulses to where it was on 75% of the time and off 25% of the time, we wouldn't have that nice over square root of 2 representation there. So you can't say that as a blanket statement for all rectangular pulses. Let's look at current waveform, although it really doesn't matter. So let's say that we have sawtooth waves, and it takes 2 seconds to complete a single cycle of the sawtooth wave. Our effective current would be 1/2 seconds times the integral from 0 to 2 seconds. So how would we mathematically describe this wave? Oh, I guess I need to give you a maximum value, so let's call this 10 amps. So we don't want the area of the triangle, we want the area of the triangle squared, right? So how can we mathematically describe the shape of the waveform, right? Because that's what we have to square. So we have, we're looking at this guy, let's look at it only over the interval from 0 to 2 seconds because that's exactly one period. So it looks like over that specific interval, when we're ignoring everything from t is equal to 2 and greater, how would we describe this? It's a line, right? It's a linear relationship. So what's its slope? So it has a slope of 10 amps per 2 seconds, or 5 also works. 5 amps per second would be perfectly valid there. Multiplied by time. Does it have a y-intercept that we need to take care of? No. So we would square this guy. There we go. So I'm going to take, let's see. So I have 1 over 2 seconds. I'm going to take that 5 amps per second squared outside of my integral. So that would be 25 amps squared per second squared, right? If I'm moving that constant term out. And then I'm going to have the integral of t squared, excuse me, dt, which is going to be t cubed over 3. Evaluated at 2 seconds and 0 seconds. Running out of room here. So let's see. So I'm going to have 1 over 2 seconds. Then I'm going to have 25 amps squared per second squared. Then I'm going to have 2 seconds cubed minus 0 seconds cubed, all divided by a factor of 3. And so this is going to look like, let's see, 25 times 8 is 200. So 200 amps squared. And then I have 2 seconds times second squared, which is going to give me 2 seconds cubed times 3. So 6 seconds cubed. But I also have seconds cubed in my numerator. Those guys are going to cancel out. And so I'm going to have 10 over the square root of 3 amps RMS. So for these sawtooth waves, generally speaking, as long as they don't have a gap between when the next period starts, it's simply their amplitude divided by root 3. And we can shift them around and all that kind of good stuff, and we'll still get that exact same answer. So most of the waveforms that we deal with in electrical engineering, square waves, sawtooth waves, and as we're about to do, sinusoidal waves, actually have very, very trivial and simplistic effective values that we can really memorize and never have to go through it again. It's not until we get to more complicated periodic waveforms that we'll actually have to go through and calculate the effective value every time. So because we are in steady state sinusoidal analysis, it's probably of interest to us to figure out how this behaves, what the effective value is for a sinusoid. So let's say that we have V of t is equal to Vm cosine omega t plus some arbitrary voltage, excuse me, arbitrary phase angle, theta v. Our effective value will be the square root of 1 period. So what is 1 period of this waveform? It'll be 2 pi over omega, right? So I'm going to show you that explicitly, right? So we're going to deal with its cosine function here, and I'm going to arbitrarily say that the phase angle is 0, because all that would mean is that if it weren't 0, we would either shift it to the left or shift it to the right, but the length of the period would be identical. So trying to draw this thing not too terribly. So this is our definition for the period. The time it takes for exactly one cycle to occur. We can obviously measure that from peak to positive peak to peak, or negative peak to peak, or positive zero crossing to positive zero crossing, negative zero crossing to negative zero crossing. However the heck we want to do it, it's fine as long as we're looking at exactly one period. We know that omega is equal to 2 pi times the linear frequency, and the linear frequency is the inverse of the period. So if we manipulate these guys, we wind up finding that the period is being dumb. 2, why is it not writing? Sorry. 2 pi over omega. So this would be 1 over the period is going to look like omega over 2 pi times the integral over 1 period. So we can arbitrarily integrate from 0 to 2 pi over omega of our voltage waveform squared. Using that first trig identity, and the one that we used in the last class when we're multiplying a cosine function by a cosine function, we can easily see that this is going to be 1/2 Vm squared cosine theta v minus theta v, which is 0. So that actually just be 1/2 Vm squared plus 1/2 Vm squared cosine twice omega t plus twice theta v. Another room there. And I need to, nope, I don't need to close my brackets because I've already done that. All right, so we could in turn split that integral up. Of 1/2 Vm squared dt plus the integral from 0 to 2 pi over omega of 1/2 Vm squared cosine twice omega t plus twice theta v dt. Oops. Close my brackets here. Make sure my square root sign goes over this whole thing. So let's look at the integral involving the cosine function first. All right. So we have a double frequency oscillation here with some associated phase angle. So what that would mean graphically, assuming our phase angle is 0, is that we are integrating this red curve, which is oscillating at twice the frequency because it has exactly half of the period, over exactly 2 periods of its waveform, right? So what should that integral give us? So we're technically, yes, But what will we get with the original cosine function if we took the integral over one period? 0, right. Exactly half of the time it's above, exactly half of the time it's below. And it's identical, like the area under the curve that is above the horizontal axis is identical to the area under the curve that is below the horizontal axis. So this whole term right here just goes to 0. Right? When we integrate any sinusoidal function over an integer number of periods, be that 1, 2, or 77, does not matter. We're always going to find that it's 0. So I'm going to have the square root of omega over 2 pi. I'm going to take out my factor of 1/2 Vm squared here. And then I'm just going to have t evaluated at 2 pi over omega and 0. And so that is going to give us omega over 2 pi times 1/2 Vm squared times 2 pi over omega minus 0. So this term and this term cancel each other out. And I find out that I get Vm, the magnitude of my voltage waveform, divided by the square root of 2. Now, what is I believe to be extraordinarily interesting about this result is that the effective value of a sinusoidal waveform is entirely independent of the frequency of the sinusoid and the phase angle of the sinusoid. So it literally does not matter how fast the signal is oscillating, how far it's been time shifted to the left or to the right. The effective value of a cosine function or a sine function is always simply its amplitude divided by the square root of 2. And in power distribution systems across the world that utilize sinusoidal waveforms to transmit power over long distances, that means it doesn't matter if you're working here in the States where we have a linear frequency of 60 hertz, or we're operating in most of Europe that operates at 50 hertz, or we're in Japan where they use both 60 hertz and 50 hertz. We always get the exact same effective value. So let's tie this back around to the effective value for a multi-frequency circuit, okay? So let's say that we have some periodic waveform V of t is equal to some DC offset voltage plus Vm1 cosine omega 1t plus some theta V1 plus Vm2 cosine omega 2t plus theta V2 plus Vmn cosine omega nt plus theta Vn, meaning we can add an infinite number of frequency terms together, even a frequency term where the frequency omega is 0. Based on our previous result, where the average value only wound up depending on the DC terms. So effectively, all of those cross-multiplied terms get thrown out when we're looking for an average value, and we're using this stuff to figure out these effective values to calculate the average power. We would find that the effective voltage in such a situation would simply be the effective value of each of the frequency terms squared, summed together, and then we take the square root of the whole thing. So what's the effective value of a DC term? The DC term itself, right? Because it has the exact same value over the entirety of its period. So that would look like V DC squared. And then here we would have VM1 over the square root of 2 squared plus VM2 over the square root of 2 squared all the way out to VMN over the square root of 2 quantity squared. So we can, if we have a sum of a voltage signal or current signal that is the sum of sinusoids at different frequencies, this is how we can get their effective value. And as it'll turn out, this will be a very powerful tool once you learn Fourier transforms and stuff like that, where we can express any voltage signal as the sum of sinusoidal signals. So, that's all I have prepared for today. So we are going to use this in our next lecture. Today's Thursday, right? So in our next lecture, which will be on Monday, we're going to use this concept of effective values to develop complex power. It all starts with the effective value for current and voltage waveform, and then goes from there. So unless anybody has any questions, I'll see you guys on Monday.
I guess like we just like if we kept everything in terms of like variables, would it always look like that? So it would be like that times the current would also. But it could just be simplified down to like one value rather than, I don't know.
So what we're doing is we're trying to find with these effective values the average power that is being supplied to or being absorbed by a particular component or something like that. So instead of breaking everything down bit by bit and then trying to find the instantaneous power and then using that to find the average power, we have an alternate route. Now the reason why this is so important is because we can't simply, like if we're dealing with a multi-frequency circuit, we are using superposition inherently. Power is not a linear quantity because it depends on the voltage squared or the current squared, which means we cannot calculate power using superposition. We would literally have to fall back on that monstrous looking instantaneous equation and then sum all the DC parts together. This is a workaround to having to go through all of that trouble.
So would we ever be asked to act for the instantaneous power?
So the instantaneous power, typically speaking, is unimportant. Okay, so there's only a couple of times where it's ever really going to be a big deal, and that is inrush in an electric motor and things like that. And so, like once an electric motor starts operating at steady state, its power is rather trivial and constant. Well, if it's a three-phase motor, it'll be constant. If it's a single-phase motor, it'll be well defined. It'll fluctuate as a function of time, but it'll be all nice and happy. But when you turn on an electric motor, there's a quantity called the locked rotor amps. So effectively, in order to get that motor to start spinning requires a whole lot more power than it takes to actually just cause it to keep spinning, because it's got to overcome the inertia of the motor not moving effectively. That's one place where the instantaneous power is a design quantity that you have to pay attention to, because if for whatever reason you designed your system with circuit breakers that were too low to handle that inrush current, the large amount of current that causes the motor to start to spin, your motor will never turn on. But most of the analysis that we are going to do with complex power and designing systems and all that kind of stuff is they're working at steady state. So we're only going to be paying attention to these RMS values and the average power, apparent power, all that kind of good stuff, because we're looking at it under steady state conditions, not under transient conditions where things can get a little bit wonky. Yeah. So there definitely are some applications where instantaneous power is important, but the overwhelming majority of applications are paying attention to the average power quantities. Good question. Anything else? Alrighty, I'll see you guys on Monday.